So Gelman settled on referring to this third quark that he had come up with as the strange quark, and it kind of stuck. So we now have the up, the down, and the strange, and all of these weird particles that had unnaturally short lifetimes and didn't last for very long. The proton and the neutron seems to have a very, very long lifetime. They don't appear to degrade and fall apart, but some particles do. And Gelman said, well, this strange behavior of falling apart particles, it's because there's a strange quark inside it, obviously. As he needed to convince other people of other particles, he then started doing what Mendeleev had done with his periodic table all those years ago. And he started combining his quarks together in different configurations to try to predict particles that had not yet been discovered in particle accelerators. And so he started sending the experimentalists lists of masses and charges of particles that he expected to be found in particle accelerators. And some of those particles were found. And this spurred the experimentalists on to keep discovering and keep building bigger and stronger and better machines. And in doing so, they also discovered some particles that he hadn't accounted for, which led eventually to him coming up with not just 3 quarks eventually, but he needed 6. His choice of names are interesting. He needed an opposite to what had settled as the word strange. So he went to a dictionary and he looked at words that were the opposite of strange, and he settled on charm. He felt that a charming person was the opposite to a strange person. So we ended up with the 4th quark being called charm. And now Gelman was on a roll, and he presented to the world his last 2 quarks as truth and beauty. But the physicists are a conservative bunch, and they couldn't handle that. And so somebody suggested instead that we keep the T and the B, but we switch to top and bottom, which is a great disappointment to the world, I'm sure. So you might see occasionally references to truth and beauty, but most of the world refer to the last 2 quarks as top and bottom. And now all we have to do is assign them some properties. So it's Gelman's game. He can make up whatever rules he likes. The proof is whether it matches reality. This is not a new thing. You remember that Newton made up the laws of gravity, and as long as they work, we trust them. So physics isn't always a game of truth. It's a game of matching reality as closely as possible. So Gelman is assigning properties. So the up quark is assigned a charge of 2/3 of the elementary charge. And the down quark is given minus 1/3 of the elementary charge. So when we combine them together to make the proton, we get 2/3 plus 2/3 minus 1/3 is 3/3, which is 1 lot of elementary charge, positive, which is what we know a proton to have. And the neutron is minus 2/3 minus 1/3 minus 1/3, which you should be objecting to the fact that this all sounds very, very, very made up. And it is. All of physics theorizing ultimately is making stuff up. But the adjective science gets to be put in front of the word theory, a scientific theory, if the model gets tested to death. And forward, there have been literally 20,000 physicists work on this model, spending billions of dollars in every country on the planet to investigate this model, to pour a terrific amount of brain power and time and effort into verifying this model. And we have yet to find anything wrong with it. So it might have originally sprung from Gelman's imagination, but doesn't everything spring from our imagination? And we just keep the stuff that appears to be valuable. And Gelman had been through dozens of models before he settled on the quark one. And so what we tend to think really now was Gell-Mann's genius, that he actually did discover some fundamental law of how the universe works. But there are so many questions associated with this, not least of which is, why do they have charges of 2/3 and 1/3? It's not the thirdness, because the elementary charge is just what we refer to as the proton charge. So maybe we should refer to the elementary charge as what the down quark has, and say that the up quark has got 2 lots of down quark charge or something like that. We're going to keep with the elementary charge. But why should it be that the down quark and the up quark have charges that are multiples of each other? Why should one fundamental particle have the same or twice as much or 3 times as much charge as another one? If the up quark and the down quark are fundamentally different objects, why is their charge related to each other? We still have that problem. In the same way that we had it with the proton and the electron, we now have it with the quark and the electron. We'll come to electrons soon. Okay, let's just finish off the properties and introduce the strange quark. All of this stuff, by the way, that I'm talking about now about charges, quarks, this is examinable, and you should be aware of these numbers. I'll give you some exercises to do at the end of the lesson where you can practice. Then the up and the down. You remember that the universe tries to minimize energy whenever it can, and the strange quark has got way too much mass, and that's not stable. It's much more stable for the strange quark to disappear from existence and allow an up quark or a down quark to exist from some of its mass energy. And so this is why strange particles disintegrate, because ultimately strange quarks disintegrate. The lightest of the quarks. And now we start to understand a little bit about why the universe is made of protons and neutrons. It's not that there's anything special about protons and neutrons. It's that there's something special about the up and the down quark. They're the lightest quarks. And because they're the lightest quarks, all the other quarks decay into the lightest ones because they're constantly trying to offload and kind of brushing against fundamental principles of physics now that you haven't properly studied. But this idea of minimizing energy is familiar to you from such things as, why does a ball roll down a hill? You can argue it from a force perspective and talk about the force of gravity, or you can just talk about the effort of the ball to minimize its gravitational potential energy. It's got less gravitational potential energy at the bottom of the slope than it does at the top of the slope. All of force physics can be recast in terms of energy physics, and the underlying principle is always processes in the universe tend to act in a direction that minimizes energy. So that the reason that the universe isn't full of all of these strange particles is because they decay as soon as they're created. We live in a universe made of protons and neutrons because protons and neutrons are the stable particles. The other particles can exist and do get created in processes like we see in stars, but they don't get to live for very long. And so Gell-Mann provides us with an explanation for not only what are all of these other particles, they're energetic combinations of quark particles, but actually he also explains why they're not here, why the universe is only really comprised of protons and neutrons, because they're the lightest particles made of quarks, and all of the other particles do get created, but they decay away. Okay, the strange quark's also got a charge. It's got -1/3. All of the quarks have got charges of either 1/3 or 2/3, and either plus or minus. Okay, said that. You now, if you study enough particle physics, you'll now, I guess, meet what happens when particle physicists spend too much time with computer programmers. So by the 70s and 80s, particle detectors are getting so complicated that you need a computer to run them, and you need a computer program to decipher what's coming out of it. So I know many of you will have done programming, and you'll be aware of the concept of variables. Computers keep track of stuff by assigning numerical values to variables. And so you can imagine the conversation, can't you, that a particle physicist is having a pint with, it sounds like a joke, with a computer scientist, and the particle physicist is trying to explain to the computer scientist what he needs the computer program to do. And the particle physicist is saying to the computer programmer, I need you to count how many strange particles there are, because they can't go missing. You need to have the same number of strange particles at the beginning as at the end, because you can't lose the strangeness. And you can imagine the computer programmer scribbling this down on a piece of paper and going and writing their computer program, where suddenly a variable turns up in their code called strangeness, which is literally a count of how much strange particles there are. It's become a word that the particle physicists have embraced. So when asking how many strange particles are there in your particle, in your composite particle, the phrase now is, what is the strangeness of the composite particle? So meet a couple of strange particles on the right-hand side of this nuclear equation. The nuclear equation, incidentally, is not examinable. You would not be asked to explain the nuclear equation. But you might be asked to fill in the details of the quarks. So if given the left-hand side, you might be expected to fill in the right-hand side. So this is like a chemical equation. Let's track the quarks. So on the left-hand side is a particle called the pi minus, the negative pion. Particle physicists love naming particles. They take a Greek letter and add the word on to the end of it. So that's the pion. They gave up with the lambda on because that sounded a bit strange. So the one on the right is just called the lambda. Okay, so we've got the negative pion, which Gell-Mann will reveal to us is made up of a pair of quarks, an up and a down, but Gell-Mann's got his thinking hat on, and it's not an actual up quark, it's an anti-up quark. Remember, in the OCR qualification, the composition of particles by quark is not examinable. You might be asked to do something with it, but if you are, you'll be given it. So you do not need to memorize that the negative pion is made up of an anti-up quark and a down quark. There's our friend the proton, two ups and a down, and it turns out that these two particles can interact with each other. And the pion and the proton, if they get close enough together, it turns out that the quarks can rearrange themselves. And it might be that they decide that they're not happy with their lives in the pion and the proton, and that the 5 quarks might rearrange themselves and shuffle into a different pair of particles. So you can see that when the anti-up quark finds itself too near to an actual up quark, the annihilation event that I spoke about on Monday is likely to occur, and the anti-up quark and the up quark will annihilate, and they will cease to be. So you can see on the right-hand side of the equation, we've lost an up and the anti-up. They're not there anymore. But what is there instead is a flash of energy. And by Einstein's E equals mc squared, that flash of energy can turn itself into a particle-antiparticle pair. And if there's enough energy there to convert into 2 lots of mass, you can have a particle-antiparticle pair. And that's what's happening on the right-hand side of the equation. We've still got 1 up, we've still got the 2 downs, but that little flash of energy from the annihilation of the up quarks has created a pair of strange quarks instead. One's a strange, one's an anti-strange. I don't know if it was the particle physicists or the computer scientists, but they thought that it would be hilarious if a strange quark had a strangeness of -1, because that would be strange. So when counting strange quarks, they count in minus number joke. Good luck if you're going to. So count the strangeness. On the left-hand side of the equation, there is 0 strangeness because there is no strange quarks. And on the right-hand side of the equation, we've got -1 lot of strangeness for the strange quark and +1 lot of strangeness for the anti-strange quark. And when you add the 1 to the -1, you get 0. So strangeness has been conserved. You could ask, do we have upness and downness? And the answer is technically yes, but nobody cares. Strangeness is tracked because when strange quarks are around, strange things happen. So it's important to know if you're dealing with strange quarks so that you can expect the unexpected, such as particles with extremely short lifetimes that don't last for very long. But up quarks and down quarks don't have any exciting aspects to their nature, so nobody really cares about upness and downness, not even the computer scientists and their variables. So nobody bothers with that. But strangeness is a word you should be aware of. There's also charmness and topness and downness, but those are rarer things. And unless you're some kind of hardcore specialist particle physicist, you wouldn't need to worry about that as well. But we just want you to understand that we track stuff. We track how many strange quarks there are, and we give rules to it, like strangeness must be conserved, which basically means if you haven't got any strange quarks and you go make some, you better make them in particle-antiparticle pairs. That's all it means. It's just been put into the language that a computer scientist would understand. Okay, if all of this is sounding like I'm making it up, that's because somebody made it up. It just happens to work. So we go with it. We're not going to make apologies for how weird the universe is. We're just going to try to chart how weird the universe is and to try and get a handle on how it works. Okay. Here are some words that you have probably never heard of before, and you are probably going to muddle them up. So try to find a mnemonic that will help you to remember these words. Okay. Protons and neutrons and lambdas and pions, all of these particles that are made of quarks that aren't real particles at all. They're composite particles, like a molecule is made of atoms, and atoms are made of protons. Well, protons are made of quarks, and anything that is made of a quark is called a hadron. So molecules are made of atoms. Atoms are made of hadrons. Hadrons are made of quarks. Okay, anything made of quarks is called a hadron. Okay. Some hadrons are made of 3 quarks. The proton is 2 ups and a down. The neutron is 2 downs and an up. These are baryons. Maybe named after a Barry. I don't know. Actually, I used to know why they're called baryons. Barry means something in Greek, and I can't remember what it means. Google it, find out. What does the prefix Barry mean in Greek? I've forgotten. They are made of quark-antiquark pairs. Now, at this point, you could legitimately ask, why do they have to be a quark-antiquark pair? Why can't it be a quark-quark pair? Good question. Do you remember the strong nuclear force that I told you it took a good 30 or 40 years for people to work out the maths of? And I told you that it was called quantum chromodynamics, QCD. You may not remember that. The reason that it was christened quantum chromodynamics is because at the heart of the strong nuclear force is the concept of threeness. So in the electric force, you have got positive particles and negative particles. Charge comes in 2 varieties. Electric charge. There's positive electric charge and negative electric charge. And so when we named the different varieties of electric charge, we needed two names that were in some sense opposite to each other. So we settled on positive and negative. Turns out that the strong nuclear force affects particles that also have a charge, but it's not an electric charge for the electric force. It's a strong charge for the strong force. Now, this sounds slightly odd. So, turns out that the strong charge, and why shouldn't there be a strong charge? Why should the electric force be the only one to have a charge? Turns out that the strong charge comes in 3 varieties, not 2. So we could hardly have had plus and minus for the strong charge, because what are you then going to call the third one? So the physicists, being clever people that they are fully aware of the fact that red, green, and blue, the primary colors, combine together to make the not really a proper color at all, white. So when naming the color charge, when naming the strong charge, they settled on the names of the colors. They called them the red charge, the blue charge, and the green charge. And the rule is, just like atoms are electrically neutral because all of the positive charges have attracted negative charges to them, the rule with the strong force is that particles must be colorless, the equivalent of strong neutral. They need to cancel each other out. So you can cancel 3 quarks out by having a red quark, a blue quark, and a green quark. No, they're not real colors. And if you could see a quark, it wouldn't really be blue. But the only way you can cancel out the color of a pair of quarks is if one of them is a red quark and the other is an anti-red quark. So you might have a blue up quark with an anti-blue down quark. Important that you don't have an up with an anti-up of the same color, because they would annihilate. But you can have an up with an anti-down as long as they are both, one's say blue and one's anti-blue. We are far off the specification now. I just wanted you to have a sneak peek, a little look at why we could only have quark-anti-quark pairs and not pairs of quarks. Again, this should sound a lot like I'm making it up because it's all made up, but it appears to be true, so we're going with it. Okay, hadrons made of quark-anti-quark pairs are called mesons. So there are 2 types of hadrons, baryons and mesons. Baryons, an example would be the proton and the neutron. Mesons, an example would be the negative pion that we just saw a moment ago. And so the question then would be, are there more types of hadron? Is it only baryons and mesons? Well, this lesson is entitled The Standard Model of Particle Physics. And the reason that it's called the Standard Model is because it's the bit that everyone accepts. However, there are research groups scattered across the planet who are actively researching that question. Are there other types of hadrons other than 3 quarks and pairs of quark-anti-quark pairs? Are there other types of hadrons? To be clear, no particle accelerator on the planet has ever detected anything other than baryons and mesons. Not once, not ever. And to put that into context, CERN detects 1 billion particles per second, and it's been in operation since 1960. So in the 60 years, detecting 1 billion particles a second, we've never discovered anything except a baryon and a meson. But maybe our machines are just rubbish. So there are research groups all over the planet that are investigating other types of hadron, theoretically. and predicting their properties and what a machine would have to be designed to do in order to detect them. But we are only discussing the standard model. So nobody knows is the answer to that question if there are other types of hadrons. You need to understand what those three words mean, though. Okay, let's have a look at the baryons. This is just for you to see them. This is just collections of baryons. So there's combinations of 3 quarks, all the different combinations. A mathematician has sat down and worked out all the permutations of ups and downs. And then you'll notice, for instance, that over here we've got 2 downs and an up making the neutron. And then over here we've got 2 downs and an up making not the neutron. It's still a neutral particle. That's what the 0 means. But this is the lambda. Why is this? It's because these particles can be in excited states. So if you take a down quark and give it quite a lot of energy, it ceases to behave like a neutron. It's still 2 downs and an up. But if you saw it in a machine, you wouldn't recognize it as a neutron because it wouldn't be behaving like a neutron because of the extra energy that its quarks have. And therefore, it's not only that the quarks can combine in different formations, but they can combine in different formations with different energies, which leads to the hundreds of different composite particles that we think we have seen in detectors, but actually it's just because our detectors can't look closely enough. If you're interested in particle physics, by all means read up about these things, and these Greek letters are the names that the particles have been named after, and these are the configurations of the quarks that make them up. We've got some mesons as well. I wouldn't worry too much about the middle ones. If you want to ask me later how we've managed to have some ups and some anti-ups and some downs and some anti-downs and all the rest, feel free to linger at the end. But I just wanted you to see it because some of you will be interested in this kind of thing, and some of you will go away and read about quarks and particle physics and quantum mechanics. And these are things you will see when you read them. Some of you may also want to go on to university and study these things more. But the last 2 slides aren't examinable. Okay, you will note that I have been very quiet on the subject of electrons for the last 3/4 of an hour. And that's because electrons are not hadrons. Electrons are not made of quarks. Electrons are the equal to quarks. They are also believed to be fundamental particles. They are not believed to have anything inside them, like quarks. We think that they are truly fundamental objects, the building blocks of the universe. But it turns out that those clever experimentalists, while observing all of those baryons and mesons in their machines, they saw a fair amount of electrons get collected as well by the particle detectors. And they saw lots of electrons, lots and lots and lots of electrons. And then they saw some heavy electrons. By all means, they look exactly like electrons. They behave like electrons. They do everything an electron does. They're just heavier than electrons. And so we knew about the electron, but it turns out it's got a slightly overweight sibling, the muon friend called the muon. And the muon has got an even heavier friend called the tauon, which sounds a bit weird. So people use for the electrons, and it seemed unfair to call them the electrons when the muon and the tau are every bit as important as the electron itself. So we invented a new name, which is also from the Greek, and I also can't remember what lept means. Look it up. So we call these particles the leptons. They are the the fundamental particles that go hand in hand in step through the universe with the quarks. But then we found, and we're going to need to talk about this in a lot of detail because you need to know the backstory to the neutrino, but we found some more particles. It took us a long time. Neutrino is Italian for little uncharged one. Neut for neutral, ino like bambino. So it's a little uncharged one. It's very, very, very light. It has, well, in the standard model, it has 0 mass, but actually the standard model is very likely to get updated in the next 5 to 10 years, because there does have a finite but very, very small mass. But in a standard model, the neutrino is considered to be massless at the moment. Because it is uncharged, it doesn't experience model 0 mass. It doesn't experience the gravitational force. And it turns out it doesn't experience the strong force either. So this invisible little particle isn't actually able to interact with regular matter, which is why we spent such a long time not noticing it. We need to have a longer chat about neutrinos because they're a story in their own right. But it turns out that every lepton has a neutrino friend. And so the bracket neutrino was expanded to include the neutrinos as well. Pretty much, if you create yourself an electron, you're going to create yourself a neutrino with it, which is why they've all got subscripts. If you make an electron, you produce an electron neutrino. If you produce a muon, you produce a mu neutrino. And if you produce a tau, you produce a tau neutrino. Like I said, we need to have a longer chat about neutrinos. But what I want you to see now is that there are 6 quarks and there are 6 leptons. I've mentioned this person before. If you're looking for a book to read during the lockdown and you like physics, but you'd like a light-hearted read and you'd like to chuckle to yourself a little bit while doing it, you can't put a foot wrong by buying Surely You're Joking, Mr. Feynman, by Richard Feynman. Feynman was incredible. You should read all about his life, but to give you the highlights, at your age, he was writing to professors at university and working out nuclear equations for his spare time while a teenager. I think he wrote his first nuclear equations correctly when he was 13 years old. He modeled how fission reactors work with the uranium fissioning. 13 years old. Feynman is probably one of the world's last polymaths, which means that he understood anything that you told him. Biology, chemistry, physics, art, music. The brain inside his head, if every human on the planet had Feynman's brain, well, we'd be in the stars by now. The guy was just a magnificent human being with a sense of humor and a life outside physics as well. Like 10 people in one. Feynman used to walk down the corridor at Caltech and without even breaking stride, just with a glance through his colleagues' open doorways at their blackboards, he would spot algebraic mistakes in their writings on their blackboard. And without even pausing, he'd just shout through the door as he went by, "You've forgotten to square your 2," or something like that. Feynman died in the 80s, and he is quite possibly the greatest physicist ever to walk the planet. Greater than Einstein, greater than Newton. It just hasn't been long enough since his death for history to put him on the pedestal that he needs to be on. If you've never heard of Richard Feynman, please read Surely You're Joking. He would never write a book himself. He dictated story after story after story to his best friend, who recorded them all and then wrote them down for him and published it as his memoirs. It's a very funny book, and he had a very rich and exciting life. Read the book. Surely you're joking, Mr. Feynman. However, what did he contribute? Well, he's the guy that gave us the rules of the strong nuclear force and quantum electrodynamics, which talks about leptons, and then prompted everybody else to invent quantum chromodynamics to talk about the strong nuclear force. And you might see diagrams like this, which are called Feynman diagrams, which is an entire branch of mathematics that he invented in order to do quantum mechanics with. And rather than use algebra, he used a diagrammatic notation. You can see why if you look under the middle picture. That's what the algebra looks like for the picture above. You can see why he preferred the diagrammatic notation to the algebra. But Feynman basically gave us the rules. Gell-Mann gave us the quarks. Feynman gave us the rules for how the quarks interact with each other. And for that, we now have the predictive power to show that Gell-Mann was correct. So he's the last person for a long time, because when Feynman gave us the rules of quantum mechanics, quantum electrodynamics, and quantum chromodynamics, the next 50 or so years was basically spent working out what it all meant. Einstein's relativity was nothing compared to what Feynman gave us. And so you are the generation of young physicists that are actually coming out of the tail end of what Feynman did. And we are now ready for the next big step. And it's already been tentatively taken. In 2013, the Nobel Prize was awarded to Peter Higgs for that equation. And if we manage to get to CERN this year, you will see that in the gift shop, everything has that equation printed on it. The mugs, the caps, the t-shirts, the posters, everything has that equation on it. If you're an educated enough physicist, that is the most famous equation in the world. And if you ask a physicist what they mean, they'll give you a one-word answer. That equation describes everything. Everything. That equation has hidden inside it all of electromagnetism, all of the nuclear forces, and the V term on the end is doing its best to include gravity. Not quite perfectly yet. But that is the equation of physics. Every force law that we have ever discovered is inside that algebra. And it is the life's work of Peter Higgs, who's the guy on the left in that picture, and his collaborator, Englert. That equation is difficult to interpret, but hidden inside it is the prediction that there exists another particle. And the other particle will stick to the quarks and the leptons like treacle. And it will cling to them and drag them back and try to prevent them moving. Peter Higgs basically predicted an explanation for mass. He said that it's not a fundamental property of particles at all, that all particles are massless. They have to push this extra particle out of the way, that this extra particle is flooding space. It is all around us like a treacle all the time. It is surrounding you right now, and when you try to move your hand, you have to push this particle out of the way, and that is why you have to push. It is why your hand feels heavy when you move it. Peter Higgs is upset to his core that the world decided to call it the Higgs particle. He is the most shy, unassuming, introverted, modest person you will ever meet. And if you talk to him and you refer to the Higgs particle, he will blush as red as can be in the face and go find a cupboard to hide in. He is embarrassed to his core that it is called the Higgs particle. But that is what he predicted. And the reason he got his Nobel Prize in 2013 is because that is the year that CERN discovered it. And it was very exciting if you were teaching physics or learning physics at that time, just 7 years ago. Right, this is your graphic of the standard model of particle physics. All matter in the universe is comprised of some of the 6 quarks, up, down, charm, strange, top, and bottom. Some of the 6 leptons, the electron, the muon, the tau, and their respective neutrinos. Behind them all is the Higgs boson, the Higgs particle, which is making it difficult for them to move and giving us the illusion of inertial mass. And then thanks to Feynman, the process by which the quarks and the leptons interact with each other. And we need to talk about that separately, I guess. But what Feynman did was to carry on Einstein's path. Einstein said, you know that guy Newton who invented the gravitational force? Well, guess what? There's no gravitational force. There is motion in a straight line through a curved space-time geometry. And that's what general relativity is. It says that there's no such thing as the gravitational force. There's just really weird space. Well, what Feynman said was, you know what? There's no such thing as any force. When one object pushes on another object, it's not because of a force. It's because one particle throws an intermediary particle at it. So imagine you and I are walking down the street and I lob a tennis ball at your head really hard. When it hits you, you are going to bounce to the side. You are going to feel as if I pushed you away, as if I exerted a force. But there was no force. There was a tennis ball bouncing off your head, which knocked you sideways. And what Feynman said to us was, whatever you think is a force, it's actually you being machine gunned with some tiny little invisible particles. And you know what one of them is. There it is, top right. It's called the photon. You've met that before. We also have the Z and the W. There are actually 2 Ws. And then, well, physicists and their wacky sense of humor, we needed a particle responsible for the strong nuclear force that was gluing the quarks together in the nucleus. So why not, hey? Let's add the word on to the end of glue. So we have the gluons. There are 8 of those. So 8 gluons, 2 Ws, that's 10, 1 Z, that's 11, 1 photon, that's 12, the Higgs boson, 13, plus 12 quarks and leptons, that's 25, plus their antiparticles takes us to a grand total of 50, which you might think is getting back up to the heady days of 200 unknown particles, but we genuinely believe that the entirety of the universe, with all its complexity and all its processes and all of its bigness and its smallness, the entire shebang can be entirely explained using the interaction of those 50 particles and Feynman's equations of quantum chromo and electrodynamics, together with Einstein's theory of gravity. We think that that is the entirety of physics. And at this point, we might be thinking about giving up and going and putting the kettle on. But we've been here before. We thought at the turn of the last century that we'd figured out the physics of the universe with Newton's laws and Maxwell's equations of electromagnetism. And it took just 15 years to show how wrong we were. So nobody's resting on their laurels with the standard model. We know there's work to do. We know that there's lots of stuff about it that we don't understand. And in particular, we know that we don't understand how gravity interacts with these particles properly. So you live in exciting times if you want to continue the journey of the standard model of particle physics. However, you need to be aware of 2 things. One, progress will be slow, expensive, and done in teams of 10,000 colleagues. There will be no individual glory in particle physics. You have to have $1 billion machine to do anything in particle physics as of this century. And so the days of one person getting all the glory are gone. Two, it's incredibly, incredibly useless. There is nothing that you can find out about a quark, a lepton, or a gluon that will change the world. Nothing. This is true blue skies physics. However, the journey is often more exciting than the destination. And as we have discussed in class, with some of you, the World Wide Web, mobile phones, broadband, MRI scanners, satellite technology, all of this is a byproduct of blue sky thinking when people were trying to find out something for no reason other than it's fun to know stuff. And this is why governments fund blue sky projects, not because they care about the blue sky project itself, but because they know that if you give money to a lot of intelligent people and let them chase their dreams, you don't quite know what wonderful things they're going to make up and discover. And our society is based on byproducts more than it is of things that were created by design. So all of those wonderful people at CERN who are chasing the quarks and the leptons, it's the byproducts that they're accidentally designing and making along the way that is far more valuable to us. Right, I'm going to leave you with some stuff to do. I apologize that I have overrun by 5 minutes. Okay, you might like to find out about particle accelerators. The Stanford Linear Accelerator is now largely decommissioned, but was the world's first big accelerator. Fermilab is a laboratory in Chicago in America. It was the next big accelerator. Note the circular shape rather than the linear shape. But Fermilab was mothballed in the 90s when CERN came online properly. And like I say, I do hope that we still get to go. I'm hoping that EasyJet are running flights and that the hostel is taking bookings and that we are able to be there. I think it's 50-50 at the moment. We'll see how we go. But you can certainly go to CERN's website and find stuff out. However, the easiest way to find more stuff out is to spend your time working your way through this website. This website was produced by Berkeley, which is one of the Ivy League universities in America. And Berkeley have provided this. Its reason for being is to take high school students across the Gulf to undergraduate level particle physics study. So you are high school students, and some of you will be considering taking the step to undergraduate physics. And this website was created for you by real particle physicists with government funding. It's an excellent website, and it starts you off as if you know nothing, and it takes you through to first year university level particle physics. You can dip in and out, you can jump from section to section, you don't have to do it in order. You could just dip in and have a look at the up and the down quark, which is all you really, and the strange quark, which is all you really need to know in terms of your OCR A level in physics. But I would love for you to spend an hour at least of your remaining time this week just playing with that website, the particleadventure.org. Know that. If you still want to steer on stuff to find stuff out while you're there, why don't you go through that website and see if you can get an understanding for these words, some of which I have talked about today, some of them I haven't. So just go through the particleadventure.org until you have a thorough understanding of those words. In terms of your exam, just to be crystal clear, it's only the top line and the fourth line that you actually need to know anything about. Hadron, baryon, meson, lepton, quark, electron, neutrino. Everything else has been a sideshow. Okay, that covers the tail end of chapter 24. I would love for you to spend time this week on particleadventure.org. So what I am going to do is not teach you anything new next week. I am going to send home some past paper exam questions, and I just want you to spend next week consolidating. So if you've missed any of the live lectures, or if you haven't understood any of them, you've got a week next week where you can watch them back, make some more notes. If there's anything from chapters 23 and 24 that you haven't understood, you'll be able to go back over that. Any questions you haven't yet done, you'll have next week to get them done. And for those of you that are completely on top of everything, I will send home, like I said, some past paper questions, and you can have a really good go at that. And then towards the end of next week, I'm going to ask you if you feel ready for me to try a kind of semi-formal assessment. If I send home a Google quiz version of a end of topic test. We're not at the end of the topic, so I'll make sure the questions are appropriate. But just so that I can get a feel for how you've done, it'll have been a month of online lectures by then. We'll have done 8 hours of this video lessons. So maybe it's time just to see how you're doing and do an assessment. Obviously, I won't know if you do it with your book open or not, but it would be nice if you took it seriously. So we're going to take a little pause, spend this week, the remainder of it, having a little look at particleadventure.org or reading 24.3 and 4 in the textbook. And then next week, lots and lots of questions and consolidation and making sure everything's fine.